Hello everybody, Mr. Rubo here. Today we are looking at 2.2, which is change in linear and exponential functions, very similar to 2.1, but now we're looking at the functions as opposed to the sequences. Okay, so last section, kind of speaking of, we learned that arithmetic sequences behave like linear functions, and that geometric sequences behave like exponential functions. Okay. And so that's what we're going to look at today. So that format that we had before, if we had arithmetic, we wrote kind of two different forms we had. We had the initial plus the common difference times the n. Well, that is slope-intercept form, which I have mentioned before. And then if you had it the other way where you were given a specific point, this kind of translates to point-slope form. And then geometric sequences, on the other hand, they are in our exponential format. The first way was, hey, if you were given the initial point, you would just write this equation. It corresponds to a times b to the x. Or another way of thinking of it is a times r to the x, where r is that common ratio. You'll kind of see those interchanged, but just realize whatever the base of your exponent is your ratio that you're going up or down by. And then we had the very similar function for our sequence here. So g sub k times r to the n minus k. It also works for functions saying y sub I, saying whatever y value it was, r, and then x minus x sub I, and it'd be that corresponding one. Very important to know that geometric sequences, exponential functions, arithmetic sequences go with linear functions. Yeah. And so here's kind of our checklist, if you will, of the different types, or what makes them different, I guess I should say. So obviously functions are different, but then over equal length input value intervals, the output values change at a constant rate. Okay. Where in exponential, over those same values, the output changes proportionally. Okay, meaning that they change by the same multiplier, where linear is based on addition. Right, so our slope is based on addition, where the change in y for exponential is based on multiplication. And so if you have 2 points, you can write the equation of linear function, exponential function, arithmetic sequence, or a geometric sequence. And if you have more than 2 points, you can determine what we have. So here, example 1, we're just asked to determine if it could be linear, exponential, or if it's a different option. Right, quadratic is another option we've talked about previously, but there's other like logs and things like that do come up. But they just care linear, exponential, or neither. All right. So first thing, look at your your x values first, and see, okay, we are going up by the same amount. So equal length input value intervals. Perfect. We can now check just the y's. We don't have to do anything extra. If that's not the case, then you do have to do a little extra work. But most of the time, it will be the case, as you've kind of seen in this class. And now we just need to see, okay, are the y values changing by a constant rate, meaning changing by addition or subtraction, or are they changing proportionally, meaning are they being multiplied by the same value? So we just start looking. That's a -2. Multiplication wise would be what, 5/7? Well, let's check the addition and subtraction, because that's always the first thing you want to check, because it's easier. And we can see we just keep subtracting 2, so this one is linear. And the reason why is over, of course my pen stopped writing. I'll just type it, it'll be neater than my handwriting. So it's linear because over equal length input value intervals, output values decrease at a constant rate. And that would be a good enough reason to state why it's linear. Again, because it's a constant rate and not a proportional rate. Okay, well, thanks for watching. Have a good day.